All right, good evening and welcome to our evening science seminar for special occasions such as this. I'm glad you guys didn't trip on the event horizon on your way in as well. Of course, you'll notice that when you get back to your dorm rooms, everybody else will look younger than you. Anyway, that doesn't matter. So we're here today to discuss recent news announcements with respect to the detection of gravity waves. And we have with us two very distinguished physicists who will be explaining to you in terms that you can understand what gravity waves are, why they are, and what it means to you as a person. Okay? We have with us tonight Dr. Steve Ball, who is the chair of our department. Dr. Ball has many degrees here. He's got a bachelor's degree from Baker University. And what do you think he got his bachelor's degree in?
Physics.
Yes. He also has a PhD from the University of Kansas. And what do you think that degree is in?
Physics.
Physics. Not just physics, but high energy physics. So this is why Dr. Ball is such an enthusiastic lecturer. Our other speaker today is Dr. Edward Hamilton. He has a great name for a physicist. Dr. Hamilton has a bachelor's degree in something which he didn't mention on here. It's chemistry, wasn't it? Yes?
Yes, among other things.
Hamilton was at one time a chemist, but then apparently he saw the light. Oh, Dr. Hamilton graduated from the same undergraduate institute that I did, Baldwin College. He also has a master's in physics, I assume, from the University of Colorado, and a PhD in physics from the University of Colorado, in addition to some postdoc time at Northwestern University. So both of these guys are well versed in what we'll be talking about tonight, and you guys are exceedingly blessed to have them here such that they can explain to you what this all means. Because years from now, when you're remembering your Laterno days, you'll remember that time when gravity waves were detected, and Dr. Ball and Dr. Hamilton explained it all to you. Let's give them a warm. Before we get going, I gotta ask you guys to turn off all your Wi-Fi. Okay? Because Wi-Fi in Glasgow is not as good as Wi-Fi in other parts of the campus because it's the first place to have Wi-Fi. So if you can turn off your Wi-Fi so it doesn't interfere with our recording of this seminar, that would be very much appreciated. All right. Thank you.
Okay, thank you so much, Dr. DeBoer, for that introduction. I appreciate your kind words. I also want to thank everybody who came out here this evening to listen to us give a presentation about some important scientific research that I just heard about for the first time a couple of weeks ago. I know when the announcement was made, it was made live on the internet, and I brought one of my students into the office. We sat down and listened to the announcement, and we thought about playing that announcement for you, but it was kind of a long announcement. They thanked a lot of the people who provided funding to them, and we felt like it might be better to do a shorter synopsis that gives you the big idea right here, and then we'll delve into some of the scientific ideas behind this big idea in just a second. I think the other reason why Dr. Ball picked out this little video clip is because it has a German accent behind it, and it kind of makes him nostalgic for his days back in Germany. So let's go ahead and play this without further ado, and then we'll go ahead and give a presentation about some of the ideas behind this.
Over 1 billion years ago, in the galaxy, over 1 billion light years away, there were two black holes steering space-time. Hi, I'm Simon, your Dark Cosmos Explorer. These are the two black holes, but first, let's talk about space-time. Space-time is a flexible fabric our universe is made out of. We experience the curvature of space-time every day as gravity, but space-time can also be noisy due to a vast number of reasons. And there can be waves, at many different shapes and frequencies, gravitational waves. There are plenty of sources for gravitational waves. Basically, all accelerated matter produces these ripples in space-time, and so do our two black holes. While orbiting each other, gravitational waves at twice the orbital frequency radiate away from the center of origin. These waves carry away energy from the binary system. As a result, the orbit shrinks, the two black holes speed up, they get closer and closer, and the orbital period becomes shorter and shorter. Frequency and amplitude increase over time, until finally the two event horizons touch and the two black holes merge into one. But let's back up a bit. This is how our gravitational wave signal looks like. It propagates at the speed of light in all directions and travels uninterrupted throughout the entire universe. The signal may have originated in a supercluster of galaxies some 1.2 billion light years away. It passed millions of galaxies in cosmic voyage before finally entering the Virgo supercluster, our home. Currently, it's passing the Milky Way galaxy. Back in 2015, on September 14th, at a time of 9:50 and 45 seconds UTC, it hit Earth. The two international laser interferometric gravitational wave observatories, LIGO Livingston and LIGO Hanford, both having just finished a major hardware upgrade, picked up the signal. They measured the tiny fluctuations in space-time along their 4-kilometer-long arms. Here's what they saw. Computer algorithms later separated the signal from instrumental noise. The gravitational wave signal lasted for some 100 milliseconds. It arrived at Livingston, Louisiana first, and 7 milliseconds later at Hanford, Washington State. The initial signal frequency was 35 Hz, which increased up to 150 Hz. We only know roughly where it came from, between 0.7 and 1.6 billion light years away, somewhere in the direction of the Dorado constellation. But the signal shape was exactly as predicted 100 years ago by Einstein's general theory of relativity. It tells us that two black holes have a mass of 29 and 36 times the mass of our Sun. The final orbit only took 13 milliseconds. A real-time playback of the event would be quite short. And we know that the final black hole is about 62 solar masses. This is the very first time a gravitational wave has ever been detected. Many more detections will follow and will help us to better understand what's going on out there in the dark cosmos. Thumbs up for the age of gravitational wave astronomy. If you enjoyed this video, subscribe to our channel, and if you've got any questions, use the comments below. Thanks. Cheers.
Okay, resuming the presentation from the slides right here, let's go ahead and move forward and think about what we do and don't know about the cosmos in which we live already. The visible universe is the universe that we can see using radiation. Initially, that radiation was only light. We had telescopes. We pointed those telescopes at the heavens, and we could see the visible light, red, green, blue. That was part of the spectrum that our eyes were intended to see. But as our technology became more sophisticated, we could look beyond that. We could look into the ultraviolet and the infrared. We could look into the radio wave spectrum and all the way up into the X-ray spectrum and discover amazing things that we never knew were happening. And the visible region of the spectrum, the universe we live in, seems like a stable place, but the farther up you go in energy, the more you see incredibly violent and exciting processes playing out before our eyes. And you can look farther with technology as well. This is the Hubble Ultra Deep Field right here. This is the most powerful telescope ever created. It's up in space, so it can be above the Earth's atmosphere and not have atmospheric interference. And this picture right here that at first looks like a picture of a bunch of stars is actually a picture of galaxies. Every single dot that's on this screen over here is a galaxy just like our Milky Way galaxy that contains billions of stars. And this square over here is actually only a tiny fraction of the night sky. You can see it over here next to the moon. There's a tiny little fraction of the night sky, an apparently empty region of the sky that we turned a telescope on and discovered a wealth of galaxies. Absolutely every color, all sorts of shapes, and all of those things are just a tiny bit of the night sky. And so the visible world is an astonishingly rich place, a place that we haven't even begun to fully appreciate. It's absolutely full of these enormous, monstrous galaxies. Yet, the visible world that we can see is only a small fraction of the things that are actually out there. Beyond the visible stars we can see, there are all sorts of things that are invisible because they don't emit light. And if something doesn't emit light, there is nothing that we can do to see it up until now. As a result of theoretical models, most scientists believe that the amount of the universe that's made up of invisible stuff, what we call dark matter, is about 80% of the universe. So that's to say 80% of the stuff out there is completely invisible. And it's full of absolutely enormous, monstrously large objects, and just kind of like this giant Leviathan over here devouring the Kraken, they're actually in the process of doing things that are very much like giant monsters eating each other. Over here we've got a picture of what you can actually see. Here we can see a time sequence as stars go through their development. Here's early stars, and here's some fully formed stars over here. But what you see is different than what's there. What's there is actually this complete skeleton on which the stars are being hung. The stars are being pulled together. The dust and the gas that make up the stars and the solar systems that form around them are being drawn inward by the gravitational force that's exerted by all of this dark matter that we can't see, all of this invisible stuff out there. And it fills in a much larger region than the stars do themselves. You can see that this star right here is surrounded by a bunch of other stuff that isn't illuminated at all. And so the question becomes, what is all this stuff? If 80% of the mass of the universe is invisible to us, it would be nice to know what it's actually made of. So there are a lot of different theories floating around as to what dark matter might consist of. And all these theories are speculative. None of them have been proven wrong up to this point, but all of them have some potential questions that they raise. Some people propose the idea that dark matter might be made of some really unusual, exotic particles, particles that we haven't observed yet, that only weakly interact with the world around them, but still produce gravitational force. And the question would be, well, how do we see them? What are they? What kind of particles are they? Maybe they're things like asteroids or planets or stars that haven't fully ignited like brown dwarfs, but when we look around us nearby in this region of the galaxy, we don't see very many objects that look like that. Certainly not nearly enough of them to make up 80% of the mass of the universe. Neutron stars, there are a bunch of those out there. They're very dense and they are invisible, but the universe is still a pretty young place, and we don't really expect that there are that many neutron stars out there. So one plausible candidate, one place that you get a lot of mass would be black holes. Black holes can be incredibly massive. Scientists believe that not only are there black holes with about the mass of the sun, or even larger than the sun, there are black holes that have masses that are vastly larger than the sun, at the heart of many, many galaxies. And those black holes are completely invisible to us in any direct way, because by definition, what makes a black hole is it produces so much gravity that even light can't escape from it. That means that in some very literal sense, it's invisible. So how would we perceive the existence of a black hole like this? First, you can look at the rotation of galaxies. The speed at which a galaxy rotates, and every spiral galaxy like ours is rotating around its center, is going to be dependent on how much mass is in the center of that galaxy. If you have more mass in the center of the galaxy, you can sustain a higher rotational velocity of the stuff that's out in those spiral arms. And you can see that the prediction that you would get based on the amount of actual mass that we observe from stars is much slower than the measured rotation of our galaxy. What that implies is there must be some extremely massive entities at the heart of our particular galaxy. And that's true of all galaxies. Another way you can observe things gravitationally is by using what's called gravitational lensing. Now, every time a ray of light emerges from a star or a distant galaxy, that ray of light travels along what it thinks is a straight line to reach us here on Earth. But we know that from the theory of general relativity, things that are straight lines are actually following what we call a geodesic in space-time. What that means is the path that they follow can be curved because space and time themselves are being curved by the forces exerted by gravity. And as a consequence of that, it's possible for two different rays of light to travel along what appear to be two separate paths and arrive at the same place. If you look away from Earth, you can look at this ray of light and look at this ray of light, and it feels like you're looking at two separate objects. But what you're seeing is double vision. You're seeing two copies of the same object side by side, and we interpret that as whatever this object was, the rays it produced were being bent and curved around something that was in between, and whatever was in between bent those rays of light enough that they came to the same point on the other side. And from that we can infer the amount of mass that makes up whatever object is between us and the thing that we're trying to observe. So both of those are indirect ways that we can infer the existence of extremely massive objects that would otherwise be dark and impossible for us to observe. All this was proposed over 100 years ago by this guy over here. If you've heard of any one physicist, you probably heard of Albert Einstein. And he's justifiably famous for a number of different things, but in our particular context, it's the theory of relativity, and in particular the theory of general relativity, that matters to us here. This thing down below is the Einstein field equations, and these equations right here govern the curvature of space-time by massive objects. And that's a pretty strong claim to make, the idea that gravity doesn't just reach out and affect objects, but gravity actually changes the structure of space itself. You can think about it, of course, this is a two-dimensional picture as opposed to the real three-dimensional world in which we live in, but you can think about it as being like on a trampoline. If you go down below the trampoline and pull it from below, and then you try to roll marbles along the top of it, those marbles will actually go along curving paths, and the curvature of that surface is analogous to the way in which space-time itself is being curved under the influence of gravity, except space-time, of course, is being done in not just 2 dimensions, but in 4 dimensions at once. I'm going to go ahead and turn things over to Dr. Ball at this point and let him talk for a bit. So I'll bring him up here so he can talk to us about the LIGO experiment that was done.
Well, I was enjoying listening to Dr. Hamilton. I guess I'll have to do something here tonight. Anyway, welcome. I'm glad all of you came out this evening, and this is exciting. This is big news. I'm going to try to convince you that this is opening up a whole new window on looking at our universe that we haven't had before up until now. And so that's why we're excited to do this. And a little bit on Albert Einstein here. Over 100 years ago, he comes up with this famous equation. This is kind of interesting. It's over here talking about space-time itself, the curvature of space-time from regular Euclidean geometry. This is that famous, where is it now? There's that famous cosmological constant term that has to do with his attempt at cosmology. And over here on the right-hand side is the term that talks about matter and energy density tensor of the universe. So the key idea that space and time itself is intimately linked to matter and energy. There's a whole new way of looking at gravity from Newtonian gravity. Newtonian gravity, you have 2 masses that are attracted by a force of attraction between them. And this is a whole new way of looking at it. There's no force per se in this kind of picture. It's masses are simply responding to the curvature of space-time induced by the other mass. And that's what allows us to do a lot of different interesting calculations with general relativity. But to get gravitational waves, you have to accelerate. You have to have a change in the curvature of space and time in order to get gravitational waves to be produced. And so where are you going to find a way to change space-time real quickly? Well, one way would be orbiting binary pulsars, neutron stars that are in close proximity to each other, that are orbiting to each other at a very rapid time frame. And when this was first proposed as a way to detect gravitational waves indirectly, that whole thought was in its infancy back in the early 90s. But we already had detection of binaries, and one binary system in particular proved to be a binary system of 2 pulsars orbiting around each other with just an 8-hour orbital time period. It's a pulsar, so it's emitting electromagnetic waves out of magnetic poles. It's kind of like a lighthouse sweeping in all directions. As the lighthouse goes around, the magnetic field is being swept around the central spin axis. And so mostly radio waves and other electromagnetic radiations being emitted by the pulsar, that's what you're detecting. However, indirectly, you can infer those gravitational waves being emitted if the orbital period's being decayed. And it's losing energy somehow. And via Isaac Newton, it shouldn't lose any. It shouldn't lose any. Its orbit should not decay at all, according to Newtonian gravity. But according to general relativity, gravitational waves are being emitted because space-time is being distorted. And so as those masses are being accelerated, they're emitting very low level, very, very hard to detect gravitational waves. But we infer the existence of those gravitational waves as they ripple away from this orbiting binary pulsar system via the radio signals that we receive from the pulsars. And sure enough, you want me to talk about this now or later? Okay, I'll let Dr. Hamilton get back to this in just a moment. But in 1993, these two guys, Joseph Taylor and Russell Halsey, were awarded a Nobel Prize in physics for their test of general relativity using the binary system, in which they saw the orbital period being decayed via the pulses of radio waves that we're receiving here on Earth. And the general theory of relativity predicts exactly what we observe for that orbital decay of that system. And so they were using the giant 300-meter Arecibo radio dish to observe this. And so they got some very good data over 3 decades of data taking. And you can see that, according to Isaac Newton, it wouldn't decay at all, and yet general relativity is predicting exactly what we're seeing here. And so this was a major vindication of general relativity as a test, the most stringent test of general relativity compared to Newtonian gravity. You can see there's a world of difference. So general theory of relativity has been vindicated, and furthermore, the inference that gravitational waves is the reason why this is losing energy. But we haven't detected them directly, just an indirect inference, okay? So I'm going to give it back to Dr. Hamilton. He's going to tell you a little bit more why gravity waves are so hard to detect.
Okay, let's take this backwards a little bit. Yeah, one of the questions that I came up with that I felt like this talk should answer is, why is it so easy to detect ordinary radiation, electromagnetic radiation, like light that we see with our eyes, and so much harder to detect these gravitational waves? Gravity seems like a really important force in the formation of the universe, and so it's a little bit surprising that the waves that are associated with it would be so difficult to detect. You'd think that if gravity is important, the waves should be an easy thing, an obvious thing that we should be able to see right away. What I've done over here is given a picture of how waves are created by an antenna. You can see this antenna right here has charges that are being sloshed back and forth. You take a bunch of electrons, throw them on one side, then you take the same electrons, rip them off, and send them over to the other side over here. As they get thrown back and forth, they make an electric field. And the electric field is an alternating field. This is generated by an alternating current. As a consequence of that, as the field flips back and forth, a wave is being generated. The wave spreads out away from the antenna, and as that wave is spreading out away from the antenna, it's filling up all of space with alternating electric fields, and we know by Maxwell's equations, also alternating magnetic fields as well. As a consequence of that, we have all these fields that can spread out, and of course they reach our eyes, and the electric fields interact with electrons that are inside the molecules that make up the retina of our eyes, and as a result of that, an electric signal goes to our brain, and we're able to see whatever it is that we happen to be looking at. Why is it so much harder for that process to occur with gravitational waves? Why don't we have eyeballs that can see gravity instead of eyeballs that can see light? And I came up with a few reasons why that would be true. Compared to electromagnetic waves, first of all, the fields that are being generated by the electromagnetic forces are much, much stronger. If you look at the force that's generated by the number of protons that exist in a standard object like this electrostatically versus the force generated gravitationally, the protons that make this up would generate a much larger amount of force than the gravitational force. The reason why we don't ordinarily recognize that those electrostatic forces are so strong is because they tend to cancel out with each other. We have equal numbers of positive charges and negative charges, and they neutralize each other. But if you separate them out like this, if you move all the negative charges over to this side and all the positive charges over to this side, you can make very powerful fields as a result of that. The fields that you produce right here are vastly more powerful than gravity in terms of being able to create forces that you experience. The second reason I came up with is also due to the fact that electric charges come in these two separate flavors that we think of as positive and negative. Gravity doesn't do that, right? There's no such thing as positive mass and negative mass. There's just mass. And as a consequence of that, you can separate out positive and negative charges by making one end of the thing positive and the other end of the same thing negative, and create what we refer to as a dipole. And then you can rapidly reverse that. You can take the positive end and make it negative, and take the negative end and make it positive, and flip flip-flop your dipole back and forth. Electrons really love to run back and forth like this to opposite ends of a conductor, and as a consequence of that, you can create what we call a dipole field, a dipole radiation field. There's no equivalent process in gravitation. You can't separate out the positive bits of mass from the negative bits of mass. All you can do is make the mass wiggle just a little bit. You can make things just a little bit fatter around the middle. You can make them skinnier around the middle. And they can bump back and forth between those two configurations. But that change isn't nearly as dramatic as the change that you see in the animation over here. Finally, we recognize that electrons are really light particles, right? Electrons don't have very much mass. As a consequence of having very little mass, it's easy to swing them around from one location to another location. In gravity, the mass is the signal, and mass always carries inertia. So if you want to make a big signal, you have to move around a large amount of mass. And it's difficult to move around a large amount of mass because the large amount of mass doesn't just generate big gravitational signals. It also creates an enormous amount of inertia, which resists moving things from one place to another. And so the thing that makes gravitational waves is the very thing that makes it difficult to do the oscillations that generate those waves in the first place. I'm going to take over from here and give a few more comments on the slides after this.
All righty, let's talk a little bit about what we do expect to see sources of gravitational waves. Of course, the largest source you can think about might be black holes that are being rapidly accelerated around each other, as in a binary system of two black holes. And of course, this is what, even long before we're going to show you the signal in a little bit that we detected here recently, but this is one of the sources that we expected to see gravitational waves coming from, because you have two very massive objects that are in close proximity, orbiting each other, very, very short time frames. This is going to be emitting a strong source of gravitational waves. Now, just looking, this picture just shows you what the optical effect would be of the black holes bending the light coming from behind it. Whereas we know that it should be a source of quadrupole radiation as well. Here is the source of the gravitational waves as those two objects are in orbit around each other. Of course, it's been greatly exaggerated, and of course we put it in a two-dimensional type frame here, but you can see that space and time is rippling outward from these two objects as they're in orbit. So this is something that we expected to see when, this is why LIGO was built, in order to observe gravitational waves from sources just like this. Talk a little bit about what kind of signal do you expect to see from a binary system of two black holes that are spiraling in, losing energy via gravitational radiation. And so their orbits are decaying, and they're eventually going to merge. And that's the time when the gravitational waves are going to be the strongest. The signal is going to be the strongest as they're collapsing in, getting ready to merge together. They're in spiraling, getting closer, the signal's getting stronger, the frequency's going up. The orbital period is getting very, very, very small. How small? You're talking expectations of 35 times a second orbiting around each other to over 100 times a second. Yeah. These are two massive black holes, 150 kilometers across, and they're moving at nearly half the speed of light. And they're orbiting each other at a rate anywhere from 35 hertz up to over 100 hertz right before their event horizons touch and merge. Yeah, so that's the time when you expect to emit the strongest signal. Strain is the stretching of space relative to a given length, and that's still expected to be from where we're here on planet Earth, a very, very small signal. In fact, the first LIGO detector wasn't sensitive enough to look at any sources like this from beyond the immediate cluster, local cluster of galaxies that we were in. If it was beyond that, the signal would be too weak for the initial LIGO setup. And that's why last fall was so important when the LIGO was upgraded, and the advanced LIGO increased the sensitivity by a factor of 10 and made it possible to observe weak signals coming to us from billions of light years away. Huge, huge increase in sensitivity. And that's why we did the upgrade in LIGO last year. And so here it shows the velocity increasing of those black holes as they're it's spiraling in towards each other. The orbital distance between them, of course, is approaching one event horizon radius. Okay, here are the two LIGO detectors that were built. One in Livingston, Louisiana, and the other one in Hanford, Washington. Each of the arms of this interferometer, and I think Dr. Hamilton is going to talk a little bit about the interferometer itself and how it works, but it's 4 kilometers long. It had to be long in order for that small 10 to the minus 21 strain to be magnified up to the size of 1/1000th of the diameter of a proton. We had to get 4 kilometers just to magnify the size of that stretching to 1/1000th the size of a proton. So you're talking an extremely sensitive interferometer that had to be built, and the technology that went into that is quite amazing. Why 3,000 kilometers apart? Well, light travel time would be 10 milliseconds going from one to the other. And so we can use that. We had to have 2 detectors for a couple of reasons. One, to locate where the signal's coming from, but more importantly, if there's noises that are disturbances causing a fake signal in one, then hopefully you wouldn't see that same disturbance causing the same fake signal in the other one 3,000 kilometers away. So you're getting 2 independent checks on the same signal. They should see the same signal in both detectors. And so this is why we had to build 2 independent interferometers that far apart in order to actually see the expected signal. All right, just a couple things about the interferometer itself. I'm not going to go into a lot of technology. We don't have time, but they had to use special fused silica for those mirrors, for those test masses that were part of the interferometer. In order the thermal vibrations would be minimized, and the suspension system of these test masses, there was 4 independent suspension systems in order to dampen out any and all nearby tremors and trucks driving down the road or any other kinds of signals that false signals that might be created. You can imagine trying to dampen out that kind of noise requires quite a sophisticated suspension system. And that's what those test masses were hung on for those mirrors. And the materials that they were made out of had to be designed especially for this interferometer. And so, and the laser itself, the boost from the initial LIGO to the advanced LIGO went from a 10-watt laser up to 200 watts for the laser itself. And that had to be extremely stable. A German team was working on this to make an extremely stable laser for this interferometer. So everything had to be extremely stable so that any kind of signal that you would see would not just be produced by your equipment itself, but by some signal actually coming into your detector. And so the way it was set up was that the interferometer was set such that the 2 paths would come back together and interfere destructively in order to null out any and all possible signal if there's no stretching of space. And that is where, okay, I'm going to give it to Dr. Hamilton for explanation beyond that.
Okay. One powerful idea I wanted to make sure everyone appreciated about the nature of an interferometer like this is it represents an application of interference effects. Back when we study waves in either university physics or general physics, we talk about the way in which waves can either have constructive interference, where they line up with each other and make a bigger, stronger wave, or destructive interference, where they line up in such a way that one wave is going up when the other wave is going down, and they cancel out with each other in order to approximately vanish. You can see that pattern emerging over here based on the offset between the 2 arms of the interferometer. Here you can see destructive interference over here, and here you can see constructive interference over here. And the difference there is pretty dramatic as a result of very small fluctuations in the length of those arms. The wavelengths associated with that light are very small wavelengths, so if you make one of them just a little bit larger than the other one, you can get a very dramatic effect in terms of the variation of the intensity. You go from being in a pure destructive situation, where the signal nulls out to zero, to being in a very strongly constructive situation, where you suddenly see a great big signal as a result of the fact that one of those two paths the laser light has to travel along has gotten a little bit bigger, and the other one has gotten a little bit smaller, or vice versa. Let's go ahead and actually look at a different way, let's listen to a different way of visualizing this information. One thing that was emphasized by one of the websites I looked at that talked about gravitational waves is that they represent two different forms of sensory information about a universe in the same way that we use both sight and hearing as ways to understand the world around us. You can imagine going to a jungle and camping out overnight. As it gets dark, you can see less and less and less around you, but you can hear more and more. And the type of information you get by listening to a jungle at night is different than the type of information you get by watching the jungle during the day. And in some ways, it's a little bit more frightening. If you're out in the jungle at night, you can hear things shrieking. You can hear predators prowling through that jungle. You can hear them maybe pouncing on other animals and devouring them alive. And in some ways, that's the universe that we live in. I'm saying that not facetiously at all. We can actually listen to the sound of predators out there in the universe devouring other objects. What we have right here is some audio files. What they've done is they've taken that same data that you saw, the signal that bounced up and down and got louder and louder and bigger and bigger and bigger, and mapped it onto the human audio frequency range. These sound files right here are actual simulated data that corresponds to objects being captured by a black hole. And I want you to listen to these things. They take a little while to rev up. They're quiet at first, and then you listen, and then all of a sudden you can hear it. So let me go ahead and play one of these over here. Here it goes. There it was, right there. Right here we had two equal mass black holes. Those two black holes collided with each other. As a result of their collision with each other, as they spiraled inward, they exerted a higher and higher frequency signal. You could hear the pitch rising, and a higher and higher intensity signal. You could hear it getting louder and louder, and by listening to the dying shriek of stars or black holes as they collide with each other, we can actually learn a whole lot about the nature of their orbits. For example, this right here is an audio file that corresponds to the data being generated by some kind of a black hole in a highly elliptical orbit being devoured by a much, much larger black hole, a galactic center black hole, that was spiraling in like in a cometary orbit with many, many passes. And you'll be able to hear this thing every single time it goes right up next to the location of that supermassive black hole. Go ahead and listen to this. What you're listening to right there is the regularization in that orbit. That orbit was initially a cometary orbit. It was very elliptical. And then what happened is the energy that was being lost to those gravitational waves began to circularize that orbit and turn it into a more and more circular orbit that was smaller and smaller and smaller. So you could hear the blips going away. And instead, what happened was the emission of gravitational waves became more and more and more uniform until it finally passed the event horizon and was captured. By comparison, this is what you would actually hear. These other signals over here are slow time processes that would take place over many, many hours. They've been sped up so you can hear them in the human audio range, so you can actually get some idea of what they would sound like if they were occurring with a much higher frequency. This right here has not been sped up at all. This is more representative of what actually happened. The signal that was detected by the LIGO Observatory probably came from an event like this. This is what happened. Boop. That was it. That was the whole thing. So you can see that by comparison, this collision between two black holes that have about, I think this is 50 times the mass of the sun, two black holes with 50 solar masses still gave a tiny signal compared to the capture of a black hole by one of those supermassive giant galactic center black holes over a much longer period of time. And so the thing that we actually detected was the equivalent of a frog eating a mosquito compared to this over here, which is the equivalent of a tiger devouring some gazelle or something like that. Okay. Let's actually look at what the signal actually looks like right here. The signal that we get is a slightly noisy signal, but you can see it has the same basic features that we just heard in the audio version. You can see it starts off with some very low intensity, long period oscillations, and the oscillations get faster and faster and faster and have a higher and higher and higher intensity until they reach some limit right here where all of a sudden it very rapidly finishes, it turns off as those two things collide with each other, and then almost immediately all the production of gravitational waves damps away and they unify into a single giant black hole. You can see what's happened is they've taken the noisy data that's over here that includes a lot of background processes, subtracted off the residual right here, and then fit this to some ideal expectation of how that data ought to behave if the noise weren't present. And you can see how both of these two signals right here match up with each other beautifully. Dr. Ball mentioned that there was a time delay between these two signals, and from that time delay we can roughly predict where that signal must have originated from. We know it came in not directly along a line between the two observatories, but kind of at an angle like this. And then once you subtract out the time difference between these two, you can basically take them and overlay them perfectly right on top of each other. And the fact that these things overlay almost perfectly with exactly the same variation in frequency and exactly the same variation in intensity gives us incredible confidence that this is a real signal, that we've observed the same event at two distinct locations twice, and that that event matches up beautifully with the theoretical expectations that we have for the actual behavior of the in-spiral of two nearly identically sized black holes. Let's wrap things up here by talking about where we might go next with our observations of gravitational waves. The big drawback that we have is that on Earth you can only make things so big. And the size of your observatory is going to determine the sensitivity of the gravitational waves that you can detect. So in order to detect processes that have an even lower sensitivity than the one that we just observed, we'll have to go up into space. And so the next big project is to take the same basic idea of interferometry-based detection and launch it up into not near Earth orbit, but very far out into space. And so the separation between these things won't just be kilometers, but it'll be on the scale of the size of objects orbiting at about the Earth's orbital radius. And that project is being sent up. I think it was originally scheduled to be sent up sometime right around now, but because of funding issues over the last 5 years, they had to cancel the U.S. participation in the project, and instead it's been delayed for about another 20 years and being carried on by the European Space Agency. But someday we'll be able to send up incredibly sensitive space-based interferometric detectors, and those detectors will be able to see a vastly larger number of sources of gravitational waves. And what we're doing is, for the first time, becoming attuned to all this extra information. It's like we've been deaf all of our lives and living in the middle of a jungle, and all of a sudden we've been granted the ability to hear just a little bit. And as we hear more and more and more of the universe around us, we'll become increasingly aware not just of what the universe looks like, but of all the violent, dynamical processes that are going on around us all the time. The way in which the universe isn't just a static picture, like the pictures that we get from the Hubble Space Telescope, but is actually constantly undergoing change. It constantly is a very dynamic place, and all that dynamism is very important to us to understand the future of the cosmos in which we live. Do you have any final words you want to add to this? I'll let Dr. Ball have the last word, then we'll open things up for questions.
I don't need to have the last word here, but I just want to say, we've detected something that we expected. This is something that we expected to see eventually when we had the sensitivity to do so. So general relativity checks out. It checks out really well. But now what are we really interested in? Now we're looking for something maybe we don't expect. But now that we've convinced ourselves we can actually detect these kinds of signals, and they're real, when we see something that is unexpected, that's when we're beginning to learn something new. Remember, when Galileo first looked at the heavens over 400 years ago, and that first time looking through the telescope at the nighttime sky, he saw things that immediately disagreed with the prevailing view, right? And I have a feeling we're kind of at the cusp of something like that today. We're starting to detect things in a new way that we've never been able to see before. It's only inevitable that we're going to see something that we didn't expect. Okay? We're ready to take questions.
Okay, in the back, over there.
So if we're looking for things we're not expecting, how do we separate it from the noise that the...
Right, this was a test to see if we could separate a true signal from the noise. And true, we knew what the signal should look like. We knew what it should look like based upon general relativity. But with the sensitivity of these, we've got several of these interferometers now, all looking at the heavens together. They should all see the same signal then, if it's real. And so hopefully we'll then be able to extract whatever new signals we're looking at from the noise. And it's real, it's coming from the heavens. And hopefully we can learn what that source of that signal is. Other questions? I don't know first. Move
You
first.
said these two bodies were moving at about half the speed of light, right? So how far apart were they before they finally blobbed together? Or, you know, you said that they were moving at half speed of light and going around each other 100 times a second?
Well, it didn't actually went around each other 100 times a second. That's what the frequency got up to right before they merged.
Okay.
Because they were, this all happened within 100 milliseconds. The whole thing happened as what we're showing is that in that last 100 milliseconds that produced the strong signals that we were able to detect here on Earth. And so, you know, this is a pretty incredible event. You're seeing something that's quite dramatic, quite a strong shift in space-time to produce that kind of gravitational wave that we can actually detect from here on Earth.
How far apart were they?
Well, we followed them until their event horizons touch. And so you're talking about 150-kilometer size event horizons. And so we were following that last bit of orbital period right until those 150-kilometer size event horizons begin to touch each other and merge into one. And that's when they're getting up to half the speed of light right before they collide. So you can only imagine two objects, 30 times the mass of our sun, moving half the speed of light, colliding. That's the kind of event you're looking at here.
You said that the strength of the gravitational wave was strongest right before they merged. Does that mean that was the signal strong enough that nearby celestial bodies would have their orbits affected by it?
No, you're looking at an extremely weak signal by the time it gets to our galaxy here. And, you know, the initial LIGO had the sensitivity to see something like this if it happened nearby, within our own galaxy or our own local group. But this, we're convinced, happened over 1 billion light years away, because by the time we detected the signal here, the strength of the signal is down to such a weak level that we can infer how far away it must have taken place.
He was asking about the bodies near the black holes, not us.
Oh, the bodies near the black holes.
Right.
Oh, here's another point that I don't think we emphasize this enough, and this is pretty incredible. You start off with two black holes. One's 36 solar masses, the other one's 29 solar masses. You have a total mass of 65 times the mass of our sun. That's a lot of mass. What's the resulting mass of the final black hole that's left? Only 62 solar masses. So what happened to 3 solar masses? That's the amount that was converted. E is equal to mc squared, converted into the energy of gravitational waves. 3 solar masses of energy converted into gravitational waves. But that's up near the source, or where this is produced. Of course, as it spreads out over 1 billion light years, you're talking a signal getting very, very weak. Good question. You had any question over here?
So you had a theorized thing on what a black hole would sound like merging. Can you explain the process more on how you render such a sound?
Right. the things that you heard, of course, aren't actually noises, because we all know that in space no one can hear you scream. But what they did is they took the signal. The signal was a signal that was actually the oscillation of the arms of this interferometer right here, which is measured in terms of the construct or destruct interference going back and forth. They converted that signal into something that you could actually listen to. So they took the variation of that intensity, the modulation of that intensity, and made that into an audio signal. In some cases, they had to change the frequency substantially. So the real process had an extremely low frequency that played out over several hours, and they had to take that low frequency signal and ramp it up by multiplying the frequency by a factor of 1,000 or something like that. So the actual signal is a gravitational signal, not really literally a sound. But it's interesting to see the analogy between the information that we get from gravitational signals and the information that we get by listening to the world around us. There are many similarities between those two things. Light does a good job of allowing us to identify positions, right? If you've got light, you can very easily figure out where something is located. But sound, even though it doesn't do nearly as well at locating objects, you hear a sound, it could be over here, over here, over here, does an excellent job of explaining how things are playing out over time. Sound is a very sensitive probe of how things are changing as a function of time, and it works really well even through barriers, right? You can hear things even when they're on the other side of the wall over there, because sound travels right through solid objects, and gravitational waves work the same way. And so there are a lot of advantages to being able to listen to the world around us using these gravitational waves, in addition to see it using electromagnetic radiation. It is an analogy. We want to make sure you understand that's an analogy. It isn't literally making noises.
I understood that it was an
Yeah. Right.
Is there any way to know how far apart the two bodies started before they got to this point?
If they started too far apart, then they wouldn't come together within the lifetime of the universe. So they had to have started fairly close, and that presents some serious difficulties for our understanding of solar system formation models, how two black holes could have formed together in one system, or were they captured? Was one captured by the other through just random forces of being in a dense cluster? So that presents some serious challenges for us to understand how black holes could have formed in a binary system like that. We don't know how often that happens, and so we don't know how often we expect to see a signal like this coming from the universe.
So when we observe the sun, we're seeing like 8 minutes past when it really light produces light. So when we're observing this, what's the time delay?
Well, this happened 1.3 billion years ago, and we just now, well, last September 14th, those signals finally arrived to planet Earth from where they originated. So they happened a long time ago in a galaxy far, far away.
My view of physics is probably a little too linear, but I was under the impression that a body traveling through space would continue infinitely. But it sounds like there's energy exerted, and there's energy being lost by the travel through space if it can make waves. So is that then not actually theoretically true? That, do you understand what I'm saying? I'm not forming the question very well.
Energy's not actually being dissipated per se, it's just being spread out over a larger and larger area as it goes and travels away from the source. And so really all of this is passing right through all of space, passing through stars, galaxies. It's not really dissipating that gravitational wave energy. It's just spreading it out.
Well, I mean the original, so does it cost some of the motion energy of the original body to create a wave?
Okay, I'll try to, I think I understand the question. This merging black hole system, probably, according to our calculations, the total power emitted by this system in the last 20 milliseconds was greater than all of the power being emitted by all the stars and all the galaxies in the visible universe combined. All of it. So there's more power coming from this in those 20 milliseconds than the entire universe itself. But the energy was only 3 solar mass. only reasonable masses in those 20 milliseconds were being expended in the form of gravitational waves. I don't know if that
Yeah, I
answers-
think that makes sense. So it's comparatively small enough so that, what I'm driving at is, does every body through space, no matter how small, make proportionate waves through space? I mean, space.
Yes, people ask me, how do you create gravitational waves? Well, you accelerate mass. Does that mean if I throw a baseball, it's producing a gravitational wave? Yes, but it's extremely weak. So you're going to have to find a way to really work, to change that warping at space-time suddenly to create a significant number of gravitational waves. Time for a couple more quick questions.
So they say it travels unimpeded, so it doesn't lose any energy traveling through masses and medium?
It's not being dissipated per se when it hits something. It just travels right through it. All this stretching of space, it's happening to every object everything that comes in contact. It stretches it, compresses it. Even the Earth gets stretched and compressed as this wave moves right through it.
These waves are just sucking all the energy out of the universe.
No, it's not sucking energy out. It's just these are the waves as they travel through the universe. They're stretching and
But they
compressing
don't
it.
re-enter the other energy mediums, like light and heat.
Right. We're not mixing it with other forms of energy.
Yes, so for the detectors that would be launched into space, would those be like 4 miles long, or is there another way to do it?
You know how big those space interferometers are?
Oh, they're absolutely enormous. I mean, the space-based interferometers are designed to have separations along those arms that are more on the order of the size of orbits. So you think about putting these not in low Earth orbit, like the scale is the size of the Earth, but in high Earth orbit, like where the moon is right now. And think about the separation between distances that are in an orbit that big. And so they're currently doing some proof of concept launches. I think that's what's happening this decade to see how far apart they can put these different pieces of the interferometer arm. But they're intended to be vastly larger, several orders of magnitude larger than kilometers.
Oh, so they wouldn't be connected?
You're not connected. They're freely suspended through space. And they bounce back and forth. Yeah.
So if these instruments took maybe a decade or two to set up or something, I don't know exactly, but do we expect this, do we think this is a common-ish event, these black holes merging, and we just happen to be lucky enough to have it set up in the 20-year space that we could read the signal?
Good question. When they went to the advanced, when they finally got the advanced LIGO system running, the official start date was going to be September 18th. And they were going to have just maybe a couple weeks of engineering running before that official start date. Well, this happened September 14th, before the official turn-on date. But they said, hey, this is already real data. I guess we're already official. So, how often are we going to see these? Now, they haven't announced other signals, but it could be as often as every few weeks we see something like this now. And if we get at least 3 of these interferometers working simultaneously, we'll do a better job of pinpointing your source, exactly where it's coming from. And we'll be able to triangulate it and see exactly where it's coming from. So the future is exciting of this research, of what we're going to be able to do. Okay, I think one more question and then we'll have to wrap up here, okay? Who hasn't asked a question yet? Have you?
So what's the practical application of this?
Right, well, what we've done is we've had a new way to look at the universe around us, and that new way of looking at the universe tells us about the way in which the universe is changing. Now, if your question is there a technology you'll be able to build and sell at some point in the future, I'm not sure that's the primary purpose of the research. But if you're a person who's interested in studying the universe, if you're an astrophysicist, and all of a sudden you've been given a whole new range of tools that you can use to study all sorts of things and answer all sorts of interesting and deep important questions about the fate of galaxies, the fate of stars, the fate of the cosmos around us. And all of those questions are questions that are extremely exciting to answer, I think. Being able to come up with explanations for what all this dark matter is to me discovering something that we didn't know before. You know, that process of discovery is itself of intrinsic value. That there's the old joke about how God must really love hydrogen because he made so much of it. Well, God must really, really love dark matter because he made a lot of that as well. And the fact that we can't see something that God really loves is kind of discouraging, isn't it? And so all of a sudden, for the first time, we've been given the ability to interact with this stuff, given a new set of sensory organs, given ears for the first time, and we'll be able to explore that entire aspect of creation that we didn't understand before.
Okay, and hopefully you guys understand much more about general relativity, gravity waves than you did before. And I want to remind you that tomorrow's seminar that was scheduled for Thursday morning has been canceled because the speaker had to be out of town. But we'll be meeting again next week, I believe, next week Thursday. Let's thank our speakers one more time.